Okay, we could not cover few small portion of the Wednesday lecture, so this is something I wanted to record. As you see, our main goal is to capture the pollutants. We understood from the live lectures that contaminants can migrate at certain speed, and that's based on the retardation factors. So now that you understood how fast they are moving, what you can do about it? Most of the time, we basically make a well here at the capture zone and create a capture zone to capture all the polluted water. That way you can extract them from ground, treat them, and re-inject back. So that's the major method for treatments most of the time. That way you can protect drinking water well here. So this is drinking water well, drinking, drinking. See, there's something happen here. So this is, let's say this is your drinking water well. And you want to protect it. So what you do is you can create a capture well, a capture zone here. So this is another, and so what you do is you pump water in that capture zone and treat it that and re-inject back after here. That way this drinking water well is protected. So to do so, you got to understand how many can you capture all the water just by having one well. Sometimes you maybe need to have like multiple wells, so that means you can have to put like this and create a bigger capture zone, like it says here. So how do you determine once you know the size of the width or the width of the the plume, you should be able to determine what's the capture zone would be. So this next couple of slides you'll learn how to decide that one. So that's we call cone of depression. So cone of depressions means if you start pumping water here, all the water will there will be a gradient here, artificially gradient, because you are creating a suction to move up. So that's we call cone of depression. Means there is a cone will form. If you look from the top, there is like a windfall, no, whirlpools of water getting into it. And so your goal is to decide what is the distance, and that distance is basically the radius is basically your capture zone, because that's the water is influenced by the pumping in the system. So to derive that one, what we do is let's write this one. So amount of flow again an unconfined aquifer is a Darcy's law KADH over dr. So area is basically the area of the cylinder. The wells are usually cylindrical, so the area of cylinder is 2 pi r, which is r is the radius of the cylinders of the well, and hc is the basically cylindrical height. So that can vary based on how much distance. So SC is a variable here. So the C is for cylindrical. And then you have to solve for H. So if you put this plug this value, this will be Q equal to 2 pi um, let's say solve for R. Okay, so not R here. So this is the one I'm solving. Let me erase this one. So your unknowns are here H, C, and your variable is R. Okay, so let's see. So if you plug the if you bring this one here, let's separate variables. So dr by r, and then q is here, and you can bring the 2 pi k should be dhc times hc. Okay, and then you can integrate it. Um, if you integrate this one, you will get q by 2 pi k ln r r1 to r2 will be hc square by 2 H1 to H2. And if you put that value here, you should be able to derive that equations. So what it says that the amount of water you can pump is a function of the height of the drop of height at different distance from the well, R1, R2. Okay, so that gives you idea of how to calculate the flow rate. Or if you know the flow rate, you know the HC2, which is the cone of depressions. Okay, so let's solve these questions. Suppose a well of zero point 0.3 meters in diameter has been pumped at a rate of 60 meter or 6,000 meter cube per day. So this is Q, okay, and this is pumping well. So this is the R, radius of the actual radius of the pumping of the well. Let's say RW. An observation well located 30 meters, so that's R1, from the pumped well was drawn with a drawdown of 1 meter. Drawdown means the distance it falls from the actual height. The original water table is here, so this difference is drawdown, okay? The difference between the actual height and the original height. That's the difference is the drawdown. So this is given 1 meter. Another well at 100-meter distance is a drawdown of 0.5 meter. So what is given is your R1 is 30 meter and your drawdown, let's write equal to 1 meter, and your actual height would be the original height, which is 30 meter, minus the drawdown 1 meter. So that would be 29 meter. And R2 is 100 meters from that well. The drawdown is 0.5 meters. So H2 would be 30 meters times 0.5. So this will be 29.5 meters. Okay. The well extends completely through the unconfined aquifer of 30 meter thickness. So the thickness of aquifer is 30 meters. So let's write D, or thickness. 30 meter. Okay. And the flow is given. Q is 6,000 meter cube per day. Determine the hydraulic conductivity. Well, you know the expression of Q, then means you just have to plug the value and get the answer. So if I write it, Q equal to pi k, I'm just going to write h1 square minus h2 square divided by ln r1 by r2. So all I'm asking is k value. So what is this k? Okay, you know Q, you know H1, which is all given here. H1 is 29, H2 is 29.5. This is given, R1 is given, R2 given, everything is given. Just calculate the K. So the K value would be, if I rearrange the equation, so that would be Q times ln R1 by R2 divided by pi H1 square minus H2 square. Okay. So that's the answer. So you just plug the value, get the answers. Estimate the drawdown at the well. I'm asking what is the drawdown at this particular well. Well, think of how to do that one. Drawdown means basically S. If you know the height in the well, then means you should be able to calculate. Well, you can see how you can calculate that. Q equal to um, pi k. Let's replace H1 with H well. Okay, H well minus S2 is basically the distance, whatever the one you assume, it doesn't matter. Now let's say 20, let's say 100 meters from now, whatever that number is. So 100 meters from now, that height is 29.5 meter. And then R1, the well of the water well, diameter is this is the diameter actually, diameter of well. So that means R of well will be 1 half of diameter times 2 divided by 2, this will be 0.15 meter. So that means you can write R1 is here well 0.15 meter divided by the H2 corresponding to meters. You know the K because you just calculated before. You plug the value here. You know the Q. You know everything else. The only thing we are solving for is this. So you should be able to calculate. So that's for the confined aquifer. Let's solve for the mass balance for unconfined aquifer. Unconfined aquifer is a q equal to, again, same thing. The difference here is that the water is not actually going through the entire well. The thickness is what is coming into play. So the amount of water that can transport is not the throughout the well, only the locations, the portion of the well that is in the confined aquifer. So that's why the instead of writing here 2 pi r hc, you are just replacing sc with the thickness of aquifer. So that's b. This is thickness. Okay. And then you, again, this is much easier to solve because this you are basically solving dr by r would be would be 2 pi pk divided by q dhc. And if you do integrations, again this will be ln, but this one will be, so ln r r1 to r2 would be 2 pi bk by q hc h1 to h2. So that's why you see the solutions will be here. Again, it's just the formula. You just have to plug the value, get the answers. So you can solve the question similar just by using this concept. So now question is capture zone. Capture zone means what's the width of the capture zone? This is the width. Okay, that's the maximum width. And your goal is to find that out. Well, there is a scientist who derived this equation. So I'm just going to write that one. So the y would be this value. Okay. That says 2q over 2b. B is the velocity of water. B is the thickness of aquifer, and tan inverse. So this is the radiance, y over x. So basically, I'm asking this theta, that's the phi. So we plug this value of pi here. This is the same as phi. So you substitute that, then this equation become this value, which is easier to remember. So this is basically angle in radians, angle in radians, not degree. Okay, pi radians. So if you know this angle, you should be able to calculate. So if you think of what is the width, as the x become infinity, that means the phi, this is the another phi is going infinity. If you think, imagine this is infinity, x infinity, this phi becomes approach towards 0. When you put the phi equal to 0, this equal to 0, then this entire term become 1. So that means the y, the maximum width will be q over 2bv. That's why this y is q over 2bv. And the total width will be 2y. 2y is the total width of the capture zone, is basically 2 q over bv. That's why it's written the entire capture width is q over bv. Okay, the point is if you have one well, you will not capture. If you have two well, you can capture more and more. So that equation is given over here. The point from here you have to remember is the capture zone is based on, the capture zone is q over bv. That means if your velocity is high, velocity of groundwater, you cannot capture a lot. So the capture zone width increases if q increases, and velocity decreases and width decreases. Okay, so that's the whole idea of understanding the concept. If your groundwater is moving very fast, you will not be able to capture because it will escape before you can capture, or you need much more higher flow rate. If your flow rate increases, you can capture more and more because you can influence that water coming in. Same thing, thickness. If your thickness is a very small, that means you are a narrow zone. You can capture a lot of that in just having one well. If its thickness is very high, then one well cannot reach out to entire width. Okay. So, having said that, let's solve these questions. That's the last questions. Consider a confined aquifer having thickness of 20 B. So that's B. Okay, that's the value is B is 20 meters. Hydraulic conductivity is 1 times 10 to the power minus 3 meter per second. And regional hydraulic gradient, so that's dH over dl is 0.002. The maximum pumping rate has been determined to be this. So this is pumping rate 0.004 meter cube per second. The aquifer has been contaminated and for simplicity consider the plume to be rectangular. So you are saying that this is the pumping well and the plume is coming like a rectangular plume. Okay. Is moving this directions and you have to capture it with a width of 80 meters. So let's say this is the width of 80 meter. Okay. And locate a single extraction well so that it can be totally removed. So you are saying where this position should be so that you can capture the entire flume. Okay. So you're looking what the distance should be. Okay, so let's think of this one. If you want to capture, you just basically asking the phi, because if you know this distance, the tan phi is the width of the y divided by this distance of the x. Okay, well, I'm just going to write x, so that means. So I'm asking what is the x would be. If you know the phi, then you will be able to calculate. Well, how do you calculate phi? If one well, you know this answer here. All I'm asking is to calculate this value. I have given q, I have given b, v, everything is given. So you should be able to calculate that. Okay. Um, I strongly suggest that you look at this example in the textbook so that you know how to solve it. But I just set it up for you. So let's see. I'm just going to write it here. Y equal to q for one well q by 2 bb velocity 1 minus p by y. So this y is given here. Okay, that's the 80. That means this will be 40 if this is y. Okay, so if it is 80 is the across, then the 40 micron, this is 40. Okay, it's going to write because you might be confused here, so let me write it here. This is equal to 40 meter because the plume is 80 meters width and q is given, it's written 0. Q is given here. That's q is here and b is here. Velocity is not given, so that's another interesting fact here. What is the velocity of water? Well, velocity of groundwater well is Darcy's velocity divided by porosity. So that's a dH over dl times k divided by porosity. And dH over dl is given, hydraulic conductivity is given, and porosity is given. Where is the porosity? Let's see. Hydraulic conductivity. Has to give somewhere. Oh, I see. I'm sorry. This velocity here is Darcy's velocity. It's not the actual velocity. So this velocity here I forgot to mention. This is, if you see how the equation is derived, we are using Darcy's velocity. We're not using other velocity. This is Darcy's equations. So you don't need porosity. So I'm just going to erase this one. This is Darcy's velocity. Okay. So if you know velocity, this is Darcy's velocity. Darcy's, you can calculate that because you know hydraulic conductivity, and then everything else is given. All you have to do is calculate this phi. If you calculate phi, you calculate x, because y is given. Okay. All right, I'll stop the recording now.